Good morning. Good morning, good afternoon, everyone. And this is Tian-Li from the International College of Semiconductor Technology from National Yang Jiaotong University. And today, we are glad to share our recent demonstration of GaN-on-silicon and GaN-on-silicon poly-AlN power MIS-HEMT with a high breakdown voltage more than 1,700 volt and stable dynamic resistance, which is less than 10% increase up to the 1,000 volt. And this work was mainly developed by the previous student Baoyong Wang and the current member Yan Wei Liu, and also is under the guidance of me. Okay, so first of all, the outline of today's talk, and we will explain the motivation of this work, why we need to work on this topic, and what's the previous result. And also in the second part, we will introduce our experimental and then the device fabrication. And third one will be the results and discussion. In this case, we will mainly focus on the two different kinds of the power MIS-HEMT. One is the GaN-on-silicon MIS-HEMT, and we try with two different dielectric, which is the silicon nitride, and we develop we try to take the advantage of silicon nitride and silicon oxide, so we develop the silicon oxide nitride. And in this part, we will show the basic IDVG and basic IDVD characteristic, and also the off-state breakdown voltage and dynamic resistance, and also the PBTI. And the dynamic resistance and PBTI are the most two reliability critical reliability challenges in the gallium nitride MIS-HEMT. And the second part, we will focus on the GaN-on-silicon poly-AlN MIS-HEMT with the silicon oxide nitride. And we will also first want to show the basic IDVG and IDVG characteristic. And we characterize our offset breakdown voltage at room temperature and the high temperature as well, and also the dynamic resistance as well. And the last one is we compare with device performance in the gallium nitride based power MIS-HEMT from reported network. So as you already may know, the gallium nitride is a promising wide bandgap material power device application because of the, for example, wide bandgap and large electron density. This is because mainly due to the two-dimensional electron gas, and also the 10 times larger critical breakdown. So in general, gallium nitride HEMT are very suitable for the power switching application. However, the gate contact on top of the AlGaN is typically formed as a Schottky contact, which usually induce a large gated current. And this large gated current actually will reduce our power device performance. So therefore, in order to address this issue, it has been developed for a while that we will try to implement an insulator between the metal and semiconductor. That's how we call the MIS-HEMT. And the MIS-HEMT can reduce the gated current, and in the end, can improve the device breakdown performance. Okay. According to our previous experience, we have found that the MIS-HEMT with the silicon oxide, silicon nitride has a different breakdown voltage and also different dynamic resistance. So you can see that this is a typical breakdown voltage characteristic. And in the case of the MIS-HEMT with silicon oxide, it has been shown very higher gated current, higher off-state current in the beginning. But compared with silicon nitride, it has been shown very lower gated current, and in the end can reach to more than 2,000 volt breakdown voltage here. And we also try to compare with interface state quality by conducting the DIT measurement. And then we found out that the silicon oxide device has a higher DIT compared to silicon nitride. This suggests that silicon nitride has a better interface state density. And this can also be an explanation that why silicon nitride has a lower of steady current, which might be mainly due to the better interface state quality here. And also the third part is we also characterize the dynamic on resistance with in the device with two different dielectric. So we can see silicon nitride, although silicon nitride feature with a lower interface state density, but it actually shows a higher dynamic R compared to silicon oxide. So therefore, the different dielectric can give us a different advantage. And here you can observe that the silicon nitride passivation has a higher breakdown voltage and low interface state density. And we try to combine the both advantage of silicon nitride and silicon oxide passivation, and therefore we develop the silicon oxide nitride poly-MIS-HEMT. Okay, so the first one is experimental device fabrication. So the advantage of gallium nitride methane is we can suppress the gallium current and further enhance the breakdown voltage. And in this study, we use two different dielectric, which one is silicon nitride, another one is silicon oxide nitride. And in the epitaxy A, we use a GaN-on-silicon with a total buffer thickness of 5.2 micrometer. And then we compare with the result with the two different dielectric, which is silicon nitride and silicon oxide nitride. And in the epitaxy B, we try to use a GaN-on-silicon poly-AlN nitride buffer. And the total buffer thickness is 4 micrometer, and we'll only study the device with silicon oxide nitride. So this is typical epitaxy and device schematic. In here, we have the silicon and around 5 micrometer. So this is 5 micrometer GaN buffer, 300 nanometer channel, and 50 nanometer L-GaN and 3 nanometer GaN. And on top of this, we have the 30 nanometer silicon nitride and silicon oxide nitride. Okay. And in the epitaxy B here, we fabricate a device using GaN-on-silicon poly-AlN nitride. So as you can see, the major difference, the first one we have poly-AlN nitride, and then we have on top of poly-AlN nitride, we start to form the silicon, and then based on silicon, we start to grow the different L-GaN GaN epitaxy here. The motivation is here. The GaN-on-silicon has a large coefficient of a thermal expansion mismatch. Thermal expansion mismatch between the GaN and silicon. So we can see silicon here and GaN here. If we use a GaN-on-silicon poly-AlN nitride, actually we can have the CT match between the poly-AlN nitride and also the silicon here. And this actually has been also developed previously by a company called the Qualmix. They claim this as a QST wafer here. And in the QST wafer, they also use a poly-AlN nitride as a substrate. So the GaN and poly-AlN nitride has a better thermal CT match. So here is the results and discussion. And in this one, we will show the basic IDVG, basic IDVD, and off-state breakdown, dynamic on resistance, and PVTI as well. Okay, in the case of a GaN-on-Si with a silicon nitride and silicon oxide nitride, so we can see the IDVG characteristic with the same dimension of 100 micrometer, gate length 5 micrometer, and LGS equal to LGD 12 micrometer. So we can see that both show the very similar drain current, although the threshold voltage there's around like 3 volts different, which is might be due to the different fixed charge inside the dielectric. But if you compare to the IDVD curve, we can see the output current are very compatible in the case with silicon oxide nitride and silicon nitride. So if you try to calculate on resistance, we can get very similar on resistance in both devices. And in terms of a breakdown voltage, we characterize breakdown voltage with a different LGD, so starting from 12 micrometer to the 24 micrometer. So in the green line, which is a silicon nitride device, silicon nitride device can gradually increase the breakdown voltage with when we increase the LGD, and then the highest one we can reach is around like 1,500 voltage here. But however, on the other hand, if you compare to the silicon oxide nitride here, So in the same scale of the same dimension of 20 micrometer, so we can reach around 1809 volt, which is here. So silicon oxide nitride MIS-HEMT shows a higher breakdown voltage compared to silicon nitride. So you can also see the extraction analysis here with increased LGD. Then the silicon nitride is always lower voltage than the silicon oxide nitride. Okay, so next part is to evaluate the reliability, and then the most important reliability in the gallium nitride power device is dynamic on resistance. So we try to give the pulse from 1 volt to 200 volt. Then after each pulse, we characterize IDVD. And after we characterize IDVD, we can start to estimate on resistance here. So this is result for silicon nitride. We can see silicon nitride actually has a significant increase on resistance. However, in the case of the silicon oxide nitride, is very stable up to 2000 volt. And even more, we characterize more than the 200 volt, and we characterize up to 1050 volt. So we can see the on resistance increase less than 6% in the silicon oxide nitride device. So this study shows that the ion degradation of silicon nitride about 1.6 times of silicon oxide nitride MIS-HEMT, which is primarily due to the more electron trapping and also in the end increased dynamic on resistance. And in the case of silicon oxide nitride MIS-HEMT, the measured device still maintain default performance with less RR. And as when we pulse stress actually achieve for more than 1000 volt, is less than 6% of increase of on resistance. Okay, and furthermore, to try to evaluate the trapping inside of the dielectric, we also conduct the PBTI characteristic. So in the case of the PBTI, as we can see here, we stretch the device at the 4 volt for 100 seconds here. And in the case of a silicon nitride device, it has an obvious higher VTH shift compared to silicon oxide nitride. In the case of 1000 volt, the device with the silicon oxide nitride shows a less threshold voltage shift compared to silicon nitride, which is below 100 millivolt. And this result actually suggests that the silicon oxide nitride has a less trapping compared to silicon nitride, and shows that the silicon oxide nitride is very promising for the passivation and dielectric can use for the gallium nitride power MIS-HEMT. Okay, the next part will be the GaN-on-Si poly-AlN nitride MIS-HEMT with silicon oxide nitride. So as we have been shown previously, the silicon oxide nitride already offers the less trapping and better dynamic on resistance, and therefore we extend this study in the power MIS-HEMT on the GaN-on-Si poly-AlN nitride substrate, and then we use only silicon oxide nitride. We will still evaluate the IDVG, IDVD characteristic and breakdown voltage, and also dynamic on resistance. So in the case of this typical characteristic, we can see that the both device has a very good output current, more than like 200 milliamp per millimeter, and also a very nice IDVD characteristic here. So the threshold voltage is around minus 4.5 volt. In the GaN-on-silicon, but when we use the GaN-on-silicon poly-AlN nitride, the threshold voltage is around minus 3.45 volt. But the most important difference is that the GaN-on-silicon poly-AlN nitride has a thinner buffer. It's only 4 micrometer compared to this one's 5 micrometer. But we can still get a very similar basic characteristic. And therefore, we start to evaluate the breakdown voltage at the room temperature and high temperature here. So in the case of the room temperature, which is the blue dashed line here, so when we increase the LGD, we can see that the maximum breakdown voltage is around like the 1700 volt. But in the case of the high temperature, and then also it can be seen that the LGD, when the LGD increase, the breakdown voltage will increase. And also, the last one shows that at 150 Celsius degree, the breakdown voltage is around 1950 volt, which is higher than the room temperature. And this can be possibly attributed to the average breakdown, since the average breakdown can have the positive temperature dependence, which means that the higher temperature can give the higher breakdown voltage. Okay, so in here we also made another summary here with a different LGD, and then we compare with the GaN-on-silicon device and versus different buffer thickness. So GaN-on-silicon device, in here we have more than 5 micrometer buffer thickness, but actually in the GaN-on-silicon poly-AlN we only have around 4 micrometer here. So therefore we can see the GaN-on-silicon poly-AlN even with a thinner buffer, but can give us a same voltage breakdown voltage as like the very thick GaN-on-silicon. So similar breakdown voltage can be achieved by using a total 4 micrometer buffer thickness in the device on silicon poly-AlN substrate, indicating that this is a high quality buffer layer grow on top of silicon poly-AlN substrate. Okay, so in terms of a dynamic on resistance here, we both evaluate the RDS on in the GaN-on-silicon and GaN-on-silicon poly-AlN, and you can see that in the case of GaN polysilicon AlN, also still give a very stable dynamic arm. It's only 7% in the voltage of the 1050 volt. So the device on GaN-on-silicon poly-AlN can achieve an excellent stable dynamic arm, less than 8% increase of dynamic arm, up to 1050 volt on the post-IV measurement, which is similar as the device on the GaN-on-silicon. So therefore, power silicon oxide nitride and MIS-HEMT on silicon poly-AlN with a high quality of this buffer can achieve the better stability with a low dynamic on resistance. Okay, so last one we can have compared our work with the reported literature in the power MIS-HEMT. And in this work, in our work, we have GaN-on-silicon and GaN-on-silicon poly-AlN. We both use the silicon oxide nitride, and we can achieve the higher breakdown voltage more than 1000 volt, even close to the 2000 volt at 150 Celsius degree. And then the most important is the dynamic on resistance is very stable. It's only like 6 and 7% increase. And if you compare to the other work here, you can see that the other power MIS-HEMT has a lower breakdown voltage and also is very higher on resistance compared to our work. So using silicon oxide nitride and GaN-on-silicon poly-AlN substrate is promising to suppress the dynamic arm and achieve a higher breakdown voltage. Okay, here come to the conclusion here. So in this study, we compare with GaN-on-silicon and GaN-on-silicon poly-AlN, and if we consider only the silicon oxide nitride as a dielectric, we both can achieve for more than 1700 breakdown voltage. And also in the case of a GaN-on-silicon poly-AlN, we'll only have the 4 micrometer buffer thickness. And most important is that these two devices can give us very stable dynamic on resistance less than 7%. So in sum, using silicon oxide nitride can effectively improve the stability of VTH shift and dynamic arm. And the device fabricated using GaN-on-silicon poly-AlN substrate with a thin buffer shows a competitive breakdown voltage larger than 1700 volt and stable dynamic arm with only 7% arm increase compared to a device fabricated using the GaN-on-silicon substrate, suggesting that silicon oxide nitride and GaN-on-silicon poly-AlN are promising to enhance the performance and stability in the gallium nitride power device. Okay, thank you very much for your attention. So please feel free to contact me if you have any question. Thank you very much.